Okay, so Eudoxus approaches the problem this way. It seems very reasonable to make the following axiom. Let me state the axiom and I'll show you what it has come down to today. The Eudoxian axiom is this. Given alpha and beta with, here's the Greeks I'm using. Of course, when we read the translated text of the axiom here on page 5, it's stated in that sort of very ancient way, two unequal magnitudes being set out. Okay, what's that? Of course, to the Greeks, they're not negative, they're not zero, they're magnitudes. So it's the two positive somethings set out is defined. One, if they're unequal, one has to be bigger than the other. So that's what I have embodied here. Okay. So given alpha and beta with that property, and a ratio greater than 0, but strictly, a ratio strictly between 1/2 and 1. I'll take the straight ratio instead of this common one. But if I have a number between 1/2 and 1, then there exists a natural number such that, of course, Eudoxus wouldn't be right this way. This is the guts of the axiom. There's a natural number n such that if we continually take away the fraction r, first from beta, and then from the result, and then from the result, and from the result, capital N times. So we will be taking away repetitively that number of fractions. That can be made less than alpha. In other words, you can force the bigger one if you chop off at least half of it a finite number of times. There's always a finite number of times that you need to do that to get it below the small one, no matter how small the little one is, and no matter how big the big one is. That's the axiom for Eudoxus. When we had algebra, the abstract algebra, actually, we studied fields. And you can place more structure on a field if you insist that the elements be ordered linearly. In other words, that all the field elements are comparable to one another in some order relation. Of course, the reals and the irrationals and the algebraic numbers are all ordered by the natural order they inherit from reals anyway. So you're always dealing with ordered field when we talk about reals. The complex numbers are not an ordered field. They're a field. You can't define an order on it's consistent. Something magic about the reals where you can do that. If you have an ordered field, there's always a zero element, the additive identity of the field. And then if you pick some element just bigger than 0, in other words, to the right of the order, if you choose epsilon, any epsilon, and any m in the natural numbers, there exists, once again, a capital N in the natural numbers, such that n epsilon exceeds a field, an ordered field, has this property. Of course, it would have to be an ordered field before you write something like this and have it make sense. An ordered field with this property is said to be an Archimedean field to satisfy the Archimedean property, which really is the Gaussian axiom in the sky. And then you pick a big one and you pick a little one, they're both positive. And you can either kill this one down, so it's between 0 and epsilon, or you can pop this one up until it goes past, right? Same difference. Whenever you can do that, the field is said to be Archimedean. And some important theorems in vector space theory that sort of rely on the Archimedean property being available. If you have a non-Archimedean field, then certain things don't happen that you expect to happen with Archimedean fields. So anyway, be that as it may, that's the modern. That's what an analyst would call the Gaussian property. If we can always do this, he's talking about. To him, he probably wasn't even thinking real numbers, right? They hated the square root too, but the rational numbers to them, the quantities that can be set out, rational numbers, and the rational numbers are an ordered Archimedean field. So the Gaussian axiom is the Archimedean property operating in the restricted setting of the ordered field of rationals. He just didn't know that property was extendable, right? Because the Greeks, they were suspicious of irrationals. I don't think they like negative numbers either. People didn't get over negative numbers until about 1500. Some people are still getting over complex. Okay, so now let's see. Here's a little exercise. Let's see if we can do this. I won't be so cooperative. Suppose we have this situation, an epsilon, and the Gaussian axiom. Say that as 3 times. The Gaussian axiom says that we can show that 1 minus r to the n times m is less than epsilon for some n and an r strictly between 1 and n. So given epsilon and m, need formula for n r, need formula for n. So how are we going to do it? We say we can do it, and it seems very plausible. You know, if you keep chopping more than half of something down, what do you have at every step? Well, here's the way I could do it. 1 minus r. If r is between 1/2 and 1, strictly, 1 minus r has to be where? Below, right? So if I put brackets around things and raise them to the nth power, I get that, right? And then if I multiply by n, I have this. So we can make this less than epsilon as we are supposed to if we can make the slightly bigger thing less than epsilon. Then we don't have to worry about r anymore, right? If we can make this come true, then we're done. Pick an n so that this is true. So how would you pick an n once you get to this?